Today's problem is from the Chinese Math Olympiad and aims at finding x if 81 to the power of sine squared of x plus 81 to the power cosine squared of x equals to 30. As a first step, by divine inspiration, we notice that 81 is 3 to the power of 4 and substitute it in our equation. In fact, it's always a good idea to bring numbers larger than 10 to forms that are simpler to express. Exponents are prioritized in problems that already use exponents. This usually gives us potential to use one of the power rules of exponents in the later steps. As the next step, we realize that we can use basic trigonometric identity, which is sine squared x plus cosine squared x equals 1. So using this, we substitute in our equation for cosine squared x in our equation 1 minus sine squared x. We continue by using the quotient rule for cases when there is a difference in the exponent. A to the power of n minus m equals a to the power of n divided by a to the power of m. In our next step, we hide most of the complexity behind a new variable, u, which we define to be equal to 3 to the power of 4 sine squared x. With this useful trick, we simplified our notations and therefore our lives too. And voila! What is in front of us is none other but a second-order equation. From the coefficients of this quadratic equation, we can determine the two roots, as we know that the product of them, which we note by p, is equal to the 0th order coefficient, minus 81, divided by the second-order coefficient, 1, which gives us 81. We also know that the sum of the roots is minus the first-order coefficient over the second-order coefficient, which comes out as minus 30. We then find a working solution by writing minus 30 as the sum of minus 27 and minus 3. Note that the product of minus 27 and minus 3 is indeed 81. With this, we successfully factorized our quadratic equation. Note that the right-hand side of this equation is 0. A product can only be 0 if at least one of its factors is equal to 0. We now divide our solution into two parts. On the left side, we solve for the situation that the first factor, u minus 27, equals to 0, leading to u being equal to 27. And on the right side, we solve for the case when u minus 3 equals to 0, leading to u being equal to 3. Now we look back in time and find our encoding for the variable u. It was 3 to the power of 4 sine squared x. We express 27 as 3 cubed, and after using the equality of powers, we arrive at sine squared x is equal to 3 over 4. Meanwhile, on the right side of your screen, at the other half of the solutions, we get sine squared x equals 1 over 4. We now need to take the square root of both sides of both equations. Let us take a moment here and remind ourselves that taking the square root of a positive number can be of either positive or negative sign. Both of these, when squared, give back the original positive value. Simplifying the square roots, we have 4 trigonometric equations to solve. Sine of x equals plus square root 3 over 2. Sine of x equals minus square root 3 over 2. Sine of x equals plus a half. And finally, sine of x equals minus a half. In all cases, we are going to follow the graphical way of solving such trigonometric equations. What we mean by this is that we find solutions of trigonometric equations using the geometric definition of sine as the ratio of the length of the opposite side to the angle and the length of the hypotenuse. We start by drawing a circle with unit radius, where all points on the circumference connected with the center define a right-angle triangle. All such triangles have a unit-long hypotenuse, and the length of the relevant side will be expressed as the y-coordinate of the chosen point on the circle. Let us start with the first two of the above cases, where sine of x equals to plus or minus square root 3 over 2. In fact, one of the well-known triangles just fits our case. The right-angled triangle that has angles equal to 30 and 60 degrees have side lengths equal to a 1 over 2 and square root 3 over 2 units, while the length of its hypotenuse is 1 unit. The angle that is opposite the side with length square root 3 over 2 is 60 degrees, pi over 3 expressed in radians. Due to the features of the sine function, there is a second solution to the equation located in the second quadrant, symmetrically with respect to the ordinate. Here, x equals to 2 pi over 3. Wait a second, have we not forgotten something? Of course! The trigonometric functions are periodic, with the period length in the cases of the functions sine and cosine equal to 2 pi. Therefore, we need to add 2 pi k to each of the solutions where k is chosen to be any integer number. Moving on to the case where sine of x equals to minus square root 3 over 2, the solutions are in the third and fourth quadrants, located symmetrically to the previous solutions with respect to the abscissa. The roots found this way are appearing at 240 degrees and at 300 degrees. In other words, they are 4 pi over 3 and 5 pi over 3 radians. Please do not forget to add the other infinite number of solutions coming from the periodic property of the sine function. Now, we continue to the cases where the sine of x equals to plus or minus 1 over 2. We are in fact using the same triangle as before. The only difference is that the relevant side for us now is the one opposite the angle of 30 degrees. That is, pi over 6 expressed in radians. In the second quadrant, the symmetrically located solution is at 150 degrees, in other words, at 5 pi over 6 radians. As before here, we also need to add 2 pi k, with k being an integer, to each of these solutions, accounting for the periodicity of the sine function. In the third and fourth quadrants, we find the solutions for the equation sine of x equals to minus a half. Located symmetrically to the abscissa, with respect to the solutions we just found in the first and second quadrants, we find 210 degrees and 330 degrees to be the correct roots. These are 7 pi over 6 and 11 pi over 6 expressed in radians. Of course, as in all previous cases, the added terms of 2 pi k being an integer cannot be missing. Wow, that was a lot of different cases to handle, right? Let us just collect all the different solutions here. We have pi over 3 plus 2 pi k, 2 pi over 3 plus 2 pi k, 4 pi over 3 plus 2 pi k, 5 pi over 3 plus 2 pi k, pi over 6 plus 2 pi k, 5 pi over 6 plus 2 pi k, 7 pi over 6 plus 2 pi k, and finally 11 pi over 6 plus 2 pi k. What are the main takeaway messages of this problem? Most importantly, clean bookkeeping. Our solution has branched into 2 cases 3 times over the process, which eventually yielded 8 sets of solutions. Don't ever forget about periodicity when it comes to solving trigonometric equations. It means you ignore an infinite number of solutions. Thank you for joining me on this quest of math problem solving. See you in the next one.